Hello and welcome to the Texas A&M University SMARTS Masterclass. The topic of this masterclass session is microgrids and microgrid automation. My name is Bronec. I am the leader of the electrical engineering group at Cushing-Carroll. I have 30 years experience designing electrical systems for a wide variety of projects, including renewable resource projects, renewable energy projects, and microgrid projects in the United States and internationally. Currently, I'm working on several micro projects in Africa and Jamaica. In my free time, I help out the local FIRST robotics team. I've been a mentor on the high school robotics team for 11 years now. Cushing-Carroll is a full-service architectural and engineering firm with 13 offices across the United States. We were established in 1938, and we have been designing energy-efficient buildings for more than 80 years. We're going to cover a number of topics in today's master class. First off, we're going to talk about what is a microgrid. We're going to talk about the benefits of a microgrid. We're going to talk about the types of distributed energy resources that go into a microgrid. We're going to talk about microgrid automation. We're going to talk about a few examples of microgrid projects that Cushing-Carroll has been involved with. And we're also going to talk a little bit about the job opportunities in the microgrid field. So what exactly is a microgrid? The basic concept behind a microgrid is to place small, efficient power production resources located at a customer's building or campus where the power is consumed. In a traditional power system, 100% of the power for a facility is imported from the power grid. Utility power grids typically contain a large central power plant that could be hundreds of miles away from the consumer. Under normal operating conditions, the microgrid power production resources operate in parallel with the utility grid. In the event of grid failure, microgrids have the unique feature of being able to disconnect from the grid and continue to supply power to the customer. The benefits of a microgrid include efficient, low-cost, clean energy. Most microgrids produce power at the point of use in a more cost-effective manner than buying power from the utility grid. Microgrids also produce clean power by using renewable energy technologies, such as solar PV and other technologies. Microgrids reduce grid congestion and peak loads on the utility grid. Producing power at the point of consumption reduces the amount of power needed from the utility grid, and it'll reduce the utility grid transmission and distribution line requirements. Microgrids also can eliminate transmission and distribution line losses. Roughly 8 to 15% of energy is lost when transmitting power from a central power plant to the consumer. This is due to the long transmission lines between the consumer and the central power plant on the utility grid. Microgrids can provide on-site backup power for critical loads. This is a huge benefit to the microgrid system. The microgrid power generation devices can be configured to disconnect from the utility grid during natural disasters or utility outages and maintain power to the buildings they serve. Microgrids also can reduce fossil fuels consumption. On-site microgrid power generation is less likely to consume carbon-based fuels. And when they do, they typically have a much higher efficiency than a central utility power plant. There are a number of different distributed energy resources that make up microgrids. The most common energy generation source in a microgrid is solar photovoltaics. These solar panels produce power from the sun's rays. Another type of energy generation in a microgrid is what's called microhydro. These hydro turbines are small. They have Pelton wheels or Francis wheels, and you can insert them into a water line or divert water out of a stream and pass that water across the wheel and spin a generator to generate electricity. Another type of energy generation in a microgrid is combined heat power plants, or CHP plants. These plants use on-site combustion engines to spin a generator, or natural gas turbines to spin a generator to generate electricity. The heat from the engines can be captured and used for heating and cooling inside of a building. In a traditional situation, we buy 100% of the power off grid. A traditional large utility power plant's only about 32% efficient when you consider the transmission line, distribution line losses, and the amount of heat that is wasted out the stack of a utility power plant. Additionally, traditionally, we utilize an on-site boiler to heat the building, which is only about 80 or 85% efficient. The total efficiency with this configuration is only about 50%. Whereas with a combined heat power system, you produce power at the same time you generate heat on site. And the total efficiency of a combined heat power systems in about 75% or higher. Another type of energy generation in a microgrid is biomass generation. Biomass systems use wood or other plant-based fuels to burn in a boiler and generate steam. The steam is then used to heat the building and generate electricity using a steam-driven turbine generator. A typical fuel source for a biomass system is wood chips. Typically, these are waste chips from like a sawmill or other wood processing facility. Another source of fuel for biomass systems is small diameter logs that are not large enough for use in lumber. These logs can be ground up and used in chips for a biomass system. Cushing-Terrell has implemented quite a number of biomass systems in Montana and Alaska. Another type of energy generation is fuel cells. These fuel cells generate electricity using a reaction between a fuel source, typically hydrogen, and an oxidizing agent, typically oxygen. The most common fuel for fuel cells is natural gas. Battery storage in microgrids is a huge market these days. These battery storages become very popular because renewable energy sources like photovoltaics and wind turbines only produce power when the sun's shining or when the wind is blowing. And these battery storage systems can store that energy for use when the sun is not shining or when the wind is not blowing. Hydrogen storage is another technology that's being explored. Hydrogen storage systems produce hydrogen from the grid during low peak times or utilize a renewable energy source through the electrolysis process. Hydrogen can then be stored and utilized to generate electricity as needed using either a fuel cell or combustion engine. Hydrogen can also be utilized as a heating source. Let's talk a little bit about microgrid automation. We use a variety of tools here at Cushing-Terrell to automate the design process for microgrids. Microgrid modeling programs simulate the operation of the multiple energy sources and optimize the engineering design selection of the energy resource. These programs will predict and calculate the best time to charge the battery source. If you have a battery source in the microgrid system, they'll decide when it's optimal to release energy from the battery system. They'll dictate or predict when it's best to export power to the grid or import power to the grid. Another automated component required for microgrid to operate properly is the microgrid controller. The microgrid controller is the main brain of a microgrid system. Microgrid controllers automatically balance multiple generation sources like solar, CHP, and battery storage systems, and they use complex algorithms to determine when to purchase power from the grid, when to export power to the grid, or when to store the electricity on site with batteries, or when to discharge those batteries. Let's talk a little bit about the projects, a few projects Cushing-Terrell has been involved with. This particular project is an off-grid microgrid power system at a very remote site in Yellowstone National Park. There's no utility power at this particular site. We have two power sources. We have a large photovoltaic array that produces power, and then we also have a small micro hydro turbine that produces about 2 kW worth of power. This turbine was inserted in a domestic water line that was put in the 1950s. The water source for this line is uphill about a half mile and about 150-foot higher elevation than the main compound. The water passes through this turbine and generates electricity. Both of these power sources are utilized to charge the battery storage system at this particular site. This battery storage system is a unique system as it utilizes recycled hybrid car batteries. Toyota sponsored this microgrid project in an effort to find a secondary use for hybrid car batteries after they have reached the end of the life of in a hybrid car. These battery packs typically have a significant amount of energy storage remaining in the battery after they hit the end of their life in the car. Another microgrid project that Cushing-Terrell was involved with was a hospital on the East Coast. This particular project, we deployed 2 natural gas combined heat power systems. The 2 of them produce a little over 3 megawatts of power 24/7 and supply power to the hospital. We capture the waste heat off of these engines and convert it to hot water and pipe the hot water into the hospital, and that hot water is utilized in the boiler system, and that offsets the amount of natural gas utilized in the boiler system. We also have this system configured for what's called island mode operation. In the event of a utility outage, this system can disconnect from the grid and continue to supply power to the hospital. Another combined heat power project example that Cushing-Terrell was involved with was several ShopRite grocery stores on the East Coast. These systems were configured to generate power 24/7 using a lean burn natural gas engine. And on these projects, we captured the waste heat off of these engines and passed it through what's called an absorption chiller. Absorption chillers can convert hot water to chilled water, and we pipe that chilled water into the store, and it's utilized in the refrigeration system. This particular project we also had set up for island mode, so we can disconnect from the utility grid during the event of a power outage, grid outage, or a natural disaster like a hurricane. In fact, a few months ago during the hurricane on the East Coast, these CHP plants kept these grocery stores running, and were able to keep the frozen and refrigerated goods from perishing, which saved millions of dollars for this particular customer. Let's talk a little bit about the job opportunities in the microgrid industry. Over the next 15 to 20 years, there's going to be a tremendous amount of opportunities in the microgrid industry. The microgrid industry is predicted to grow up to $40 billion by the end of 2028. The main reason for this expansion is due to the sustainability plans that a lot of entities around the United States have committed to. In order to achieve these sustainability initiatives, there's going to need to be a tremendous amount of expansion in the electrical infrastructure throughout the United States. The reason for this infrastructure expansion is to accommodate electric vehicles. The state of California recently committed to phasing out the sale of gasoline cars by, I believe, 2035. This will require a lot of improvements to the electrical infrastructure. Also, there's a lot of sustainability initiatives that are going to reduce the amount of fossil fuels utilized in the energy industry. This will have a pretty large impact on the electrical grid as well, because a lot of what was normally heated with, say, natural gas, a lot of that's going to have to be heated with another source, such as electricity. There's going to be a lot of opportunity in the microgrid industry for electrical engineers and other engineers. That concludes our presentation for this master class, and I want to thank you for the opportunity of presenting.